intensity and frequency of incident light. Okay, how if depend of the intensity or depend of the frequency of the energy, right? The photoelectric effect to be a wave or a particle? That is the question. Probably the word photoelectric effect is new for you, but for the reason I want to review a little bit about what is the photoelectric and what is the story behind that. If you remember this one right here, what happened right here? I'm going to go to this one first. This one is a magnet, and you can see right here the magnetic field. Do you remember what happened if I change the magnetic field? That means I move the magnet, and I make the magnet go close to the wire, metal wire, okay, solenoid. See what happened? The electrons start moving, right? Okay, and then if I move this one, electron move in the opposite direction. Do you remember Lenz's law? Yes, that is what happened. Okay, remember, I'm going to show you the other video, and this one is mechanical energy is transformed to electricity. How? Is when you change, when the mechanical energy, the potential energy, converting kinetic, and this kinetic energy make a work, is doing a work on that the thing that make rotate the thing. Okay, change the magnetic field because make the magnet move. When this magnet move, changing the magnetic field, make the electron move up and down, up and down. That means alternate, producing an alternate current. If I change the intensity, it's going to change the intensity of the light. Okay, less intense, more intense. Okay. Do you remember who was the person that gave the explanation of the phenomenon? Electromagnetism, that means the connection between the electricity and magnetism? Yes, was Faraday, right? He said that the only connection, the only explanation was the speed of the light. But do you remember that he couldn't prove that mathematical? Who proved that mathematical? Yes, that was Mr. Maxwell. Remember that he said, and he formulated the equation saying that 3.0 times 10 to the 8 meter per second is the only explanation that this one happened, electromagnetism. But how is it possible that 3.0 times 10 to the 8 meter per second is the speed of the light? But light is a wave. How the wave is making particles move is not possible, right? Okay. For this time, it was not possible. But now, I'm going to introduce Mr. Professor Brian Cox. He is an amazing physicist, and I would like you paying attention to his presentation and his explanation. He explained in a way that makes everything easy. Could you please pay attention?
Now, quantum mechanics at first sight seems like a pretty strange view of the world, but it's experiments like this, the photoelectric effect, done at the turn of the 20th century, that forced us into that picture. Now, this is a gold leaf electroscope, and it's charged up. There's an excess of electrons on this plate, which causes the gold leaf to rise.
Okay, if you remember this one as the electroscope, do you remember why the leaves are separate? Exactly, because it's charged. Electron and electron, a increase of electron, they are together. The two electrons, they repel each other. Okay.
Now watch what happens when I turn a light on. The light forces the electrons off the plate, discharging it, and the leaf falls back down again.
Okay, how is that possible? The light push or remove electron, make the electron move. Light is light. Light is a wave. How the light is going to make a particle move? Right now, it doesn't make sense, right? Pay attention.
Now that's pretty easy to understand. What isn't is that the energy of the electrons that come off the plate depends not on the brightness of the light, but only of the colour. Now that...
Okay, he's saying that this one doesn't depend on how bright. Remember when I show you when it's bright and when it's not bright? Okay, depend of the color. I'm going to ask you a question. Do you think the color red, yellow, green, and blue, they have the same energy? Remember in our previous videos that we talk about it? They have different energy. Okay, they have different frequency. They have different wavelength. If they have different frequency and wavelength, that means they have different energy. That is why.
It's impossible to understand if you think of light as a wave motion. And it took Albert Einstein to come up with the correct explanation. He said that you can picture light as a stream of particles called photons, and not as a wave. And the energy...
Okay, remember now. Now Albert Einstein is saying, okay, the light is not just a wave. If not, sometimes behave like a particle. And these particles are called photon. This photon has an energy that can interact with the electron and react and move and show that they are there.
Of each photon depends only on the colour. That realization, that explanation of the photoelectric effect, lies at the heart and at the foundation of quantum theory. Einstein's explanation of the photoelectric effect presented a new challenge to scientists. Up until this time, they had explained the properties of light in terms of waves. Suddenly, it seemed that light could also behave like particles. How could this be? The resolution to this seeming paradox had to wait for three of the giants of 20th century physics, Feynman, Schwinger, and Tominaga.
Okay, what he's saying is that the light sometimes can behave like particles. That means they can interact with the electron, that they are particles. And then for the reason you can see that they move.
As well as explaining the behaviour of light, QED provided a revolutionary way to look at forces. Instead of thinking in terms of force fields, as Newton and Maxwell had done, QED explained the electromagnetic force in terms of particles. To understand how it works, imagine two electrons approaching each other. We know that they'll move apart because like charges repel.
Okay, they spread out because an electron has negative charge, and two negative charge they repel each other, right? That makes sense.
QED says that the repulsion is caused by a photon, a particle of light, being transferred between the two electrons.
Okay, now you understand why they repel, right? Okay, the electron has that capacity. Remember that Mr. Faraday said that the only explanation is the speed of the light? Then the photon is light, right?
So the photon is the particle that carries the electromagnetic force. QED proved so successful that it seemed natural to look at the quantum theories of the other forces that concern us as particle physicists, the weak and strong nuclear forces.
Okay, now I want to show you what is the photoelectric effect, how that is produced.
Photoelectric effect. The photoelectric effect refers to the emission or ejection of electrons from a metal surface in response to incident light.
Okay, if this one is a light, carries energy, right? This one has a light. But remember now we know that the light can behave like a particle. If this light behaving like a particle, then it's going to remove the particle in this metal. Okay, the particles that they can move there freely are going to be electrons.
Energy contained within the incident light is absorbed by electrons within the metal, giving the electrons sufficient energy to be knocked out of or emitted from the surface of the metal. Einstein in 1905 proposed that the incident light consisted of individual quanta, called photons, that interacted with the electrons in the metal-like discrete particles rather than as continuous waves. For a given frequency or color of the incident radiation, each photon carried the energy E is equal to h nu, where h is Planck's constant and nu is the frequency. Albert Einstein was honored with the Nobel Prize in Physics in 1921 for successfully explaining the photoelectric effect.
I'm going to ask you this one. Do you think all the light are going to be with this effect? Remember, E equal h time frequency. Frequency, okay, with that h, that is a constant, is going to produce energy. If the light doesn't have enough energy to move that electron, you are not going to see that effect. Let me show you a PowerPoint that I have here to show you some simulations. Okay. Okay, I have right here this PowerPoint. Okay. I'm going to try to make this one like that. I have this simulation right here, and then later, if we are going to try to show you the simulation in class. We're going to work on that. But what happened right here is I'm going to move this one away, and then what happened? This I'm showing you right here. This light. This one is sodium light, and then what happened is make the electron move, right? Okay, this one make the electron move because this one is light. Okay, behave like a particle this time, and then make the electron move. And then in the next slide, I'm showing you this one is the frequency. This frequency right here is the minimum frequency, okay, to move electron. Okay, the next one I'm going to try is a different color. Okay. Okay, and the next one is showing us the frequency, and then I'm going to put the simulator, and you can play with that later. But my conclusion of this one is the effect, the photoelectric effect, is the connection again between electricity and light. But in this case, the light behave like a particle. This one, this characteristic is called photon. I'm going to let you play and let you analyze the frequency and how you need a minimum energy, a minimum frequency to produce the photoelectric effect. Could you please try to play with this simulator and answer the next questions, okay? And tomorrow we are going to be working more, and I'm going to be asking more questions about this one. Thank you very much.